All right, so I'm going to walk you through the Calorimetry Gizmo Part 2. So this is Activity C for the Calorimetry Gizmo. And in Activity 1, you guys were learning about calorimeters and how they worked and the concepts of specific heat and what a calorie and a joule is, along with heat capacity. And in Part 1, you guys were doing several experiments using the Gizmo simulation to collect data for final temperatures of different substances as they were in the calorimeter. So in this part, we're actually going to be using those temperatures, and we are going to calculate how much heat was released or how much heat gets absorbed, okay, by the water in the calorimeter. Okay, so in order to figure out how much actual total heat that is, we need to use this equation here, our Q equation. Okay, I call it the Q equation because it's Q equals M times C times delta T. Okay, so the Q is heat. And heat is, remember, heat is a type of energy. And it is measured in either calories or it's measured in joules. Okay, so you'll either see CAL or capital J for the units for heat. So to figure out how much heat is absorbed or released during a reaction or just during a, when two objects are near each other of different temperatures, all right, we need to know the mass of the objects. So M is for mass. And mass is, like you know, is always measured in grams. So we'll see that in the unit G for grams. The other thing we need to know is the heat capacity, and that's how much heat is needed to raise the temperature of a substance. So metals, you'll notice, just in everyday life, like if it's a really hot day, like the metal hand railings outside of school, going up and down the flights of stairs are really hot because it does not take much heat to heat up those metal railings. They have a low heat capacity. But things like water, okay, water has a very high heat capacity. So you'll notice even on really, really hot days, a pool feels nice and refreshing because the water doesn't get heated as fast. All right, because again, water has a very high heat capacity. So the specific heat capacity is the letter C, okay, in this particular equation. And so we need to know that. We need to know how much energy it takes to heat up the substance that we're talking about. Okay, so specific heat capacity. And that gets measured in either calories per gram degrees Celsius or joules per gram degrees Celsius. Kind of just depends on which one we're working with. Okay. And then last but not least, we have the change in temperature. So remember, the triangle means change in. It's the delta sign. All right. So it's a change in temperature. And this is measured in degrees Celsius. All right. Because the specific heat is degrees Celsius. So we need to make sure that our temperature is in degrees Celsius. So these are the three things that we're going to need to multiply together. Okay, so as soon as you can identify each of these three variables, we're going to multiply them all together, and that's going to equal how much heat is needed to, heat is absorbed or released for those objects. All right, so let's go ahead and take a look at the first question in our Gizmo. So this part of the activity, its goal is to calculate the specific heat capacities of copper, granite, lead, and ice. Okay, so we're going to be using that Q equals M times C times delta T to figure out or solve for different variables within that equation. All right, so the first one says when you mix two substances, the heat gained by one substance is equal to the heat lost by the other substance. So if you remember in Part 1, when you were working with the calorimeter, you had this, container, and inside of it was water. Right. And inside the water, you guys were putting different pieces of metal. So heated up metal, right? So the metal that was heated up, the energy from the metal, the heat from the metal went released from the metal into the water, right? And so there was a thermometer on the side that measured the temperature, right, of the water as the heat from the metal goes into the water. That's what it means when you mix two substances. When you, like, for example, when you take a heated metal and you put it in water, those two things are mixing and touching each other. The heat gained by one substance, so in this case, the water, is equal to the heat lost by the other substance. So the other substance is the metal. Okay. So in this question, it says, suppose you place 125 grams of aluminum in a calorimeter with 1,000 grams of water. The water changes temperature by 2 degrees, and the aluminum changes temperature by negative 74.95 degrees. Okay, so negative just means it lost temperature, right? Or it lost heat. Temperature decreased. So it started out really hot, and then it decreased 74.95 degrees Celsius. So lost energy. All right, A says water has a known specific heat capacity of 4.184 joules per gram degree Celsius. Use the specific heat equation to find how much heat energy the water gained. So again, we're going to be using our Q equals M times C times delta T, all right, to solve this equation or solve this question. And for this one, what substance are we working with? Well, in A, it's the water, right? It says how much heat is, how much energy is gained by the water. So when we plug everything in for this equation, we want to use the water stuff, okay, the water information. Because in our paragraph up here, we are given information for both aluminum and water. So right now, we're just going to deal with the water one. So for water, we know that we have the M is 1,000 grams. So we have 1,000 grams of water, right? Our C, remember, is specific heat. We are given that right here. So 4.184 joules per gram degrees Celsius. And then we have to do our change in temperature. And if we read closely up here, it says the water changes temperature by 2 degrees Celsius. So there's our change in temperature, 2 degrees Celsius. So when we multiply all of those together, 1,000 times 4.184 times 2, okay, we're going to get how much energy has been gained or absorbed by the water. So when we do that, we get... All right, so let's take a look at part B of this problem. It says, assume the heat energy gained by the water is equal to the heat energy lost by the aluminum. Remember, that's exactly what's going on in a calorimeter. We have a container with a bunch of water in it, and we put a heated piece of aluminum in it. The heat energy from the aluminum is going to go out to the water. So whatever heat is lost by the water, so Q lost by the metal is going to be equal, right, to the heat energy absorbed by the water. So all of the heat lost by the aluminum metal is being absorbed by the water. So if we keep reading, we get the question that we're actually supposed to solve for. So it says, use a specific heat energy to solve for the specific heat of aluminum. So again, we are going to use our Q equation. Q equals M times C, the mass times the specific heat times the change in temperature. But instead of solving for heat, Okay, we're actually going to be solving for specific heat. So that's our C right here. Specific heat is our C. So we need to rearrange this equation to solve for C. So on that right-hand side, we have mass times specific heat times the change in temperature. So in order to get C by itself, then we need to divide both sides by m times delta T, right? That would get rid of this guy and this guy. So what we do to one side, we always have to do to the other side since there is an equal sign there. So we rearrange this equation so that we are going to be solving for C. So C now is going to be equal to Q divided by mass times the change in temperature. Okay, so this right here is going to be the equation that we are going to use to solve this particular question. All right, so when we are using this, we have to make sure that we are plugging in the numbers for the correct substance. In this case, it's all about aluminum in this question. So we're going to be looking for the Q, that's the heat. Remember, the heat of the aluminum lost is the same as the water gained. And we just solved how much heat was gained by the water in A. Okay, so we need to do our 8,368 joules from the first part. Okay, and then we need to know the mass of the aluminum. So up here we have here 125 grams of aluminum. And then we also need to know the change in temperature. And in this case, it says right here, the aluminum changes temperature by negative 74.95 degrees. Okay, so we are going to put 74.95 degrees Celsius. Okay. All right, so when we do this calculation, we do 8,368, that's a comma there, and then we're going to divide it by 125 times 74.95. Make sure that you put that in parentheses in your calculator so that it does the order of operations correctly. So when you do this math, you should get the specific heat of the aluminum. Now remember, we talked earlier about metals having very low specific heat. That's why they heat up and cool off so quickly. So for this, right, you're going to get an answer of 0.893. And the units are joule per gram degrees Celsius, just like we've talked about in the first slide. Okay, so here's our specific heat of aluminum, 0.893 joules per gram degrees Celsius. And right under it on your papers, it says aluminum's accepted specific heat value is 0.900 joules per gram degrees Celsius. So our calculation of 0.89 is very close to the accepted value, so we know we did it right. All right, so let's keep going. And in number 2, you guys are going to use the actual Gizmo simulation to mix 200 grams of copper at 100 degrees Celsius. So copper starts at 100 degrees Celsius with, and you're put that in 1,000 grams of water that starts at 20 degrees Celsius. And when you do that, and you click the simulation, you should get the final temperature of the water to be 21.42 degrees. So we're going to use that information in order to solve the rest of these problems, okay? So B says calculate the temperature change of each substance by subtracting the initial temperature from the final temperature. So we have two substances here. Remember, we have copper and we have water. So that's why we have two different delta T's here. So let's start with our change in temperature for water. So we always subtract final minus initial. Right? So final minus initial. And so our final temperature of the water was 21.42. And we're going to subtract 20 degrees is where we started with, right? It's up here. So we end up with a temperature change, a delta T, of 1.42 degrees Celsius. So that's going to be our answer here, 1.42 degrees Celsius. All right, and then we're going to do the same thing with copper. Okay, so our change in temperature for copper this time is going to be final minus initial. So in this case, our final temperature, again, is 21.42. Because remember, that's the temperature. That's when both of them hit thermal equilibrium. It means they're both the same temperature. Aluminum released all of its heat in order for water to come up to the same temperature as him, right? So 21 minus, and then remember our copper started at 100 degrees Celsius. Okay, so we're going to get a negative number here, and a negative number is just referring to the fact that that heat is released from the copper. Okay, so when we do that, we get an answer of negative 78.58 degrees Celsius. So that's what our temperature change should be here. So negative 78.58 degrees Celsius. Okay. All right. So we know the water heated up by 1.42 degrees Celsius and the copper cooled down by 78.58 degrees Celsius. Okay. So now let's take a look at part C and D. All right. So let's take a look at part C. How much heat energy, so we're going to be solving for Q, did the water gain? So we're going to be looking for water. So everything we're going to plug in is going to be measurements for water. So Q, remember, equals mass times the specific heat times the change in temperature. So we're going to take the mass of the water. So we have to look up at our initial conditions up here, and we see that we have 1,000 grams of water. So we're going to do 1,000 grams. Okay. Specific heat of water we've worked with before. It's always the same when we're working with water. 4.18 joules per gram degrees Celsius. Okay, and then our delta T, our change in temperature for water, remember, is 1.42 degrees Celsius. So then we just multiply all of those together, and we're going to get our Q for water, our amount of heat gained by the water. So in this case, our answer is 5,941.28. And remember, our units for Q are always joules. Or again, we can look and see that our grams are going to cancel top and bottom, and our degrees Celsius cancels top and bottom. So all we're left with is joules. All right, so C is 5,941.28 joules. All right, D says now solve for the specific heat of copper. So we have to remember that the energy from the water gained is equal to the energy that was released by the copper, right? So if the Q for the water was 5,941.28 joules, that means that exact amount of water is released, 5,941.28 joules was released by the copper. And we put a little negative sign here to represent, like I mentioned earlier, the release of energy. Okay, and then here we kind of have a invisible plus sign to represent the absorption of energy. So this guy absorbs energy. Water absorbed 5,941.28 joules, and as the copper released that same amount of energy. So when we're doing part D, we again need to solve for C this time. So earlier we rearranged our equation. We found out that C equals Q divided by mass times the change in temperature. So this time though, remember we are working with copper. So all of this stuff all of the numbers that we need to plug in are for copper now. So the Q is our negative 5,941.28 joules, right? Our mass of copper, we need to go back up here and take a look at how much mass. So it says 200 grams, so 200 grams. And then remember our change in temperature is what we figured out up here, negative 78.58 degrees Celsius. So you'll see we've got a negative divided by a negative. So in the end, we're going to end up with a positive number, which is good. Okay. So when we do our math, all right, negative 5,941.28 divided by, and then make sure again you put this in parentheses, 200 times negative 78.58. Okay, we're going to get our answer of let me do a little different color, 0.378. And remember, if we look at all of our units, none of these cancel with each other, so we just need to put it together in this giant unit, joules per gram degrees Celsius. All right, so that is for C, 0.378 joules per gram degrees Celsius. So question number 3 is exactly like question number 2. You're going to be doing the experiment with granite, and then also you're going to repeat it down here, part E, you're going to repeat it for lead as well, and you're going to be finding the change in temperatures, right? You're going to be figuring out how much heat is gained by the water, doing the exact same thing that we just did in number 2, figuring out the specific heat for granite, and then again for lead. Okay, so after doing number 2 together, you should be able to figure out number 3 on your own. All right, number 4 is a challenge question. All right, and it asks you to use the specific heat capacity you just calculated for granite. Okay, so you're going to use whatever answer you got here, okay, to help you with the next one. To determine how many grams of granite. Okay, so we're going to be solving for mass this time. So we're given initial temperature of 80 degrees Celsius. It's mixing, we're told, with 3,000 grams of water at an initial degrees of 20 degrees Celsius. The final result of the whole system, so the final result of the water plus the granite is 20.45 degrees Celsius, okay? And so you're going to be doing, all right, the same calculations that you did in number 2 and number 3, but instead of part D where it says, in number 3 where it says find or solve for the specific heat, instead of that, you're going to be solving for the mass, okay? So let me just go through the steps here. So you're going to find Q for water, right, by doing mass times specific heat times the change in temperature, just like we've done before. All right, so that's step number 1. Step number 2, okay, is to find the mass of the granite. Okay, so if we are going to rearrange our equation here to solve for mass this time, okay, we need to divide both sides by C times delta T. So our mass is going to be Q divided by C times delta T, right? So this Q comes from whatever we got, that answer that we got in step number 1. The C is going to come from whatever you calculated up here in number 3. And then obviously the change in T is going to come from here okay, when you did the experiment. Okay, so that kind of hopefully should set you up for that one right there. All right, and then I'm going to leave the extend your thinking for you guys to do to try on your own. All right, so hopefully that helps to guide you through the equations and how they work for this particular gizmo. If you have any further questions, please just email me or post on our discussion board.